Now we want to look at an example. So we look at an example where we have a binary x and a binary y, and we have three states, 0, 1, and 2. First, look at the channel if s is equal 0. I wrote it here, that's perhaps better. So if s is equal 0, then we have that py of xs of 1 is equal x0 is equal q for x equals 0 and 1. What does it mean? This means if I have the output 0 and 1, this is x, then I go with probability 1 minus q, I go to 0, with probability q, I go to 1. But if I have a 1, then also with probability 1 minus q, I go to 0, and with probability q, I go to 1. The first thing what you noticed, it doesn't depend if x is equal 0 or x is equal 1. In each case, we receive the same probability 0 and 1. With probability 1 minus q, we receive 0, and with probability q, we receive 1. That's the first case. The second state, if it's s equal 1, we have this situation. Then the probability of y conditioning on x and s of 1 is x comma 1 is equal 1 minus q. What does this mean? So let's look at this. So let's look at the case s equal 1. So let's assume we send, here's again x, we send 0 or we send 1. This means with probability q now, we go to 0, and with probability 1 minus q, we go to 1 if I send a 0. But I have the same for 1. With probability 1 minus q, I go to 1, and with probability q, I go to 0. This is the case if s is equal 1. Now let's look at the case what happens if s is equal 2. If s is equal 2, we have the case, let's look at it. We have 0 and 1, which could be sent over the channel. And with probability 1 minus p, I go to 0. And with probability 1 minus p, I go to 1. So that means the crossover probabilities that is p. That means this is a really binary symmetric channel. In this case, it doesn't depend what I send, so the output is independent of x. So therefore, we have now two ideas, so we act differently. So first, we assume that the state sequence here, ps 0 and ps of 1 is equal lambda. Then, of course, ps of 2 is equal 1 minus 2 lambda. Now we consider a binary u. That means we consider a channel from x to u in the following sense. Again, we need such a channel. So it goes this time from x to u. So we have 0 and 1, and 0 and 1. And now we choose a probability alpha, that 0 goes to 0, and 1 minus alpha, that 1 goes to 0 and 0 goes to 1. And now we do the following. If s is equal 0 and s is equal 1, then we know that it doesn't depend on x. So the idea is that we then choose x is equal s. Otherwise, if we are in the case is that s is equal 2, then we choose x is equal u. And now for this case, we can compute the rate by this formula with this u, this very special u here. So we know that the rate is bounded by, or the rate is equal to the mutual information between u and y minus the mutual information of u and s. Of course, the mutual information of u and y in this case is 1 minus, because it's the entropy of u, minus the binary entropy of that y is equal u. And if you look at the second part, that depends, of course, on S. So this is 2 times lambda times 1 minus the binary entropy of alpha. So that's just the rate formula for this channel. And if you choose this very special U here. But it turns out, if we optimize alpha, then the resulting rate turns out to be the capacity of the channel. I think that's also a good exercise to look at this in more detail, because it's not so difficult. You have to write down this channel where you have S0, S1, and S2, the 3 cases which the channel can have. And then I give you the way you have to select U. And then just calculate by our formula the mutual information between U and Y minus the mutual information of U and S, and you get the result.